Today we're going to put the calculus back in Calc 3. After a long period of introducing some of the things, some of the objects that we're going to be working with, for example vectors, and gaining intuition about vectors and understanding surfaces, we're now ready to talk about the calculus of vector-valued functions. In this particular section we'll be doing some basic differentiation and integration. The integration is useful, but I would say just to focus your attention mostly on the derivatives. The derivatives have really beautiful geometric interpretations, which we'll get to in a minute. The objectives are essentially all of these. These are mostly computational objectives. I'm throwing in an additional set of objectives here to sort of understand how the derivative definition of vector-valued functions moves to the component-wise derivative formula that we'll see in a minute. And it's really just a linearity of the difference quotient and how it moves in onto each component of the vector-valued function. To really understand the geometric interpretation of the derivative of a vector-valued function, that as sort of r of t plus delta t minus r of t, as delta t goes to 0, that kind of turns into a tangent vector between two vectors. Also to know that the velocity vector, the derivative gives the velocity vector, which is just the speed and direction of the object at that moment in time. Finally, again, to compute the integral of a vector-valued function, we'll mostly be using that to go up and down the ladder of acceleration, velocity, and position. So acceleration, velocity, and position, I can get from position to velocity with a single differentiation. I can get from velocity to acceleration with another differentiation. And I can go back up the ladder. I can go from acceleration to velocity by integrating, from velocity to position by integrating. And really the only difference between what we're learning today and what you may have learned in Calc 2 about velocity, acceleration, and position is that you're working with vectors now, and you have to kind of interpret that. All right, so as I mentioned, the big idea here is that the difference quotient is really a difference of vectors, and that as delta x goes to 0, that difference of vectors approaches the tangent to the space curve at that point. Very much akin to secant lines that you learned about in Calc 1 when you did the original sort of old style derivative. All right, let's do a bit of a flyover of the section. So as I've mentioned to my students many times over the years, when you're in doubt about how to differentiate something, it's always wisest to go back to the definition of the derivative or something that looks like the definition of the derivative. If r is a vector-valued function, like we discussed in the previous section, that means I plug in t and I get out a vector. Look at this difference quotient. Forget about the limit for a minute and just look at the difference quotient. And if you look at r of t plus delta t, you're talking about a point in time t, and you're talking about going a little bit away from that point in time and looking at the vector associated with that time a little bit away from the time t. So I have these two vectors, one right at the time t and one a little bit away from the time t, and I take the difference. Well, we know from back in when we learned about vector subtraction that this is really a displacement vector. It's a displacement vector from r of t to r of t plus delta t. It connects those 2 points. It sort of gives me the direction from this point to this point. And as we send them close together by letting delta t go to 0, what we get is a vector that points tangent to the space curve. Okay, so that's the big idea, and I'll show you a picture of that in a minute. In fact, maybe, I guess I could do that now. I have this, this little link here. Let me fire up this, this copy of GeoGebra. So here we have a little, a space curve, the black line going through space. And if I change time, I'm just moving along the space curve like that. And what we're seeing is a few vectors in this picture. One is the vector that goes to r of t. The orange vector points to the position r of t. The green vector points to the position r of t plus h. The purple vector points in the direction of displacement from r of t to r of t plus h. And you can see that when the orange vector and the green vector are close together, that corresponds to small h's. So if I take h and I make it smaller, make it close to 0, the orange and the green vectors get close to each other. And if you look really closely at the purple vector, you see that it starts to point in a direction tangent to the curve at time t, or at position r of t. And this is the big idea. And as I move t around, you can see that that purple vector moves along with it. It might grow and shrink a little bit depending on the speed of the particle along the curve, but that's basically it. If you look at the red vector, that's the numerator of the difference quotient, r of t plus h minus r of t. And it always goes from the tip of r of t to the tip of r of t plus h. That's just basic vector geometry. The purple vector is a little bit longer than the red vector in this case, and that's because it's divided by the scalar h, which is usually a small number, less than 1. What's curious about this limit, at least for differentiable vector curves, or space curves, is that as h goes to 0, the vector doesn't just explode on us, it actually approaches a limit. A finite limit, a vector that points in a particular direction with a particular length. And it's this that kind of gives us that extra information. Not only is it telling us the direction tangent to this point on the curve, but it's also telling me how fast the particle is moving at this point. The length of this vector is proportional to, or in fact tells me exactly, how quickly the particle is moving at this point in space. And if I move it around, it's kind of hard to see, but the vector lengthens down here on this part of the curve, and it kind of shortens way up here at the peak. Again, it's hard to see without just rotating it around. But what this is telling me is that it's kind of slow. The particle's kind of slow up here, and then as it goes down the length of the curve as we advance it, that vector lengthens, and we can interpret that as the particle's moving more quickly along this segment of the curve than it was along this segment of the curve. So the difference of vectors is giving me a displacement vector from one tip to the other, and as h goes to 0, that displacement vector turns conveniently into the tangent vector. Finding the derivative of a vector-valued function is pretty straightforward because everything up here is really nice, right? How do you take the difference of two vectors? You subtract component-wise. How do you multiply by the scalar 1 over delta t? You multiply component-wise. And what that amounts to, for your purposes, is this difference quotient that looks like it's acting on a pair of vectors can be interpreted as acting on each component individually. And in the limit, what that amounts to is taking the derivative in each component separately, and that's a skill that you learned in Calc 1. So differentiating space curves or vector-valued functions actually just leverages a skill that you already have, and instead of doing one derivative, you're doing 3 derivatives, 1 in each of the components, or 2 derivatives, 1 in each of the components, depending on whether it's 3 dimensions or 2 dimensions. So to find the derivative of this vector-valued function, we just take the derivative of each component. So the derivative of this component is just 3. The derivative of this component is 2t minus 4, and that's r prime. What does that represent? It tells me the speed and direction of the particle at any given time t. Cool. All right, let's carry on a little bit and look at some of the sort of abstract properties of derivatives of vector-valued functions. These are all of the things that you're used to, at least the first couple. In other words, the constant can pass through differentiation. So the derivative of a constant times a vector valued function is just that constant times the derivative of the vector valued function. Furthermore, differentiation of vector valued functions distributes across addition and subtraction. Interestingly, there's a kind of product rule. So if I have a scalar function f and a vector valued function u, there's this kind of product rule, f prime u plus f u prime. And it actually plays nicely with the dot product in a very kind of product rule way as well. The derivative of r dot u is just r prime dot u plus r dot u prime. Pretty cool. It also has, I think this is amazing, it also has a kind of product rule with the cross product. So the derivative of r cross u is the derivative of r cross u plus r cross the derivative of u. The only thing that you have to be careful about with the cross product is that you preserve the order. And whatever the order of the cross product is over here, that's the order of the resulting cross products that you get over here. So it's r cross u here, so we get r in the first slot, u in the second slot, r in the first slot, u in the second slot. That's always preserved. The chain rule works, so the derivative of r of f of t is just r prime of f times f prime of t, so that's pretty cool. And the last one is just an identity that will be useful, and we'll see this identity come up again. So again, just to recap, this linearity, it plays nicely with constants, it plays nicely with addition and subtraction, and then these rules are all sort of associated with stuff that only vectors can do. But they do, the rules do seem kind of natural and do kind of extend from the rules that you're familiar with. All right, this section sort of is a recap of the idea that I was talking about earlier. For example, in this diagram we have a circular space curve in 2 dimensions. The derivative is always tangent to the position at any given time. And you can go back to the GeoGebra app to kind of remind yourself why that works. Okay, it's useful to have some notation for the tangent vector that is a unit vector. So in general, r prime is the velocity of the particle that's following the space curve. R prime is the velocity, that is the magnitude, speed, and the direction. Sometimes we just want to talk about the direction, and that happens so often that we actually give it a name, capital T. But it's not a mystery. We're taking r prime, which is the tangent vector, the velocity, and we're dividing by the magnitude of r prime to make it a scalar, to make it a unit vector. So capital T, whenever you see that, immediately you want to think, oh, that's just the unit vector that's tangent to the curve. It erases the speed part of the tangent vector. Finding the unit tangent vector, you find r prime, you find the magnitude of r prime, and you divide, and we'll do an example of that at the end. Finally, I'll leave you with integrals of vector-valued functions. Integration, again, we're not going to do the derivation of this, but the integral of a vector-valued function from, say, a to b is just the component-wise integration from a to b. So if you want to know how to do that, just distribute the integral onto each component and do the integral, and now you're just back in Calc 2. These are skills that you have. I think more importantly is, what does the integral of a vector-valued function actually mean? And for our purposes, I think the best application or the best explanation is if you take r prime, the velocity vector for r, and you integrate it, say from a to b, what you get is the net displacement of the particle as it moved from time a to time b. This is going to enable us to go up the ladder from acceleration as a function of time to velocity as a function of time to position as a function of time. But again, just using skills that you learned in Calc 2. All right, let's hit some of the exercises, and then we'll be finished with this relatively short section. So the first thing we want to do in problem 50 is just compute the derivative of the vector valued function. I'll remind you that the derivative is merely the component-wise derivative of the function. So for example, to compute r prime of t, we're just taking the derivative of t squared, which is 2t, times the standard unit normal vector I, plus the derivative of the j component. And notice this is t e to the minus 2t, so we have to use the product rule. That's going to be first times the derivative of the second plus the second times the derivative of the first, like that. And then carry along the j unit vector. Last, not least, is the derivative of the k component. That's going to be minus, actually it's going to be plus 20 e to the minus 4t, and then carry along the k unit vector. You can simplify this a wee bit. Let's see here, e to the minus 2t times the quantity 1 minus 2t j plus 20 e to the minus 4t k. That's it. Just take the derivative component by component and we get r prime. This is a relatively straightforward computational problem. Normally, what you'd be doing is sort of interpreting this as the velocity of the position space curve. All right, let's find the tangent vector at the indicated value of t. So now it's a two-step process. We're going to find r prime of t, and then we're going to evaluate it at pi over 2. R prime of t, again, just component-wise differentiation. Negative 2 sine 2t times I plus 2 cosine t times j plus 2t k. And now we want to figure out what the tangent vector is at the specified time, r prime of pi over 2. All right, the sine of 2t when t is pi over 2, that's the sine of pi. That's 0. The cosine of pi over 2 is also 0. And finally, 2t, where t is pi over 2, is simply pi k, like that. So this vector in component form looks like this. And we would expect, I don't know what the rest of the curve looks like, but we would expect it to look like this, kind of pointing in the k direction at this point. In fact, we can see that. I put together a quick GeoGebra demo. So plotting this guy and looking at the point t equals pi over 2, we should see that the velocity vector points straight up along the positive z-axis. So taking this curve, cosine 2t, comma 2 sine t, comma t squared, that exactly matches what we're looking at here. And I plotted the whole curve. It's kind of a stringy mess. And let's look at the point at t equals pi over 2. If I take t equals pi over 2 and plug it in to the derivative function, what I get is negative 1, 2, and pi squared over 4. And if I plot that point, what I see is it's out here on the edge where the curve is sort of going and turning up to the next sort of bend. And if I look carefully at this, I can kind of imagine that the tangent vector, if I'm traveling along this curve and bending around and going up, that tangent vector is pointing parallel to the positive z-axis. Hopefully you can see that. So this is definitely representing tangent vectors. Let's do another. Let's find the unit tangent vector for the following curve. So now what's different here? You got to pay attention to the words. Now we're looking for the unit tangent vector. This is capital T of t. Well, you're not going to find capital T until you find r prime. So let's go and find r prime. The derivative component-wise is minus sine of t I plus cosine of t j minus sine of t, plus cosine of t k. So that's r prime. That is not t. How do we figure out t? Well, we have to figure out the magnitude of r prime. And that's the square root of the sum of the squares. So sine squared t plus cosine squared t plus cosine squared t square root. I can take two of these and use the Pythagorean identity. And what's left is 1 plus cosine squared t square root. And there's not really much further simplification you can do with that. Finally, the unit tangent vector, capital T, is what I get by dividing r prime by the magnitude of r prime. And I'm just going to put it out front. 1 plus cosine squared t square root times the vector minus sine t, cosine t, and cosine t. This gives me a unit vector that is always tangent to the curve for any t values, and in fact the t values here are limited between 0 and 2 pi, but for any t values for which this function is differentiable. Let's look at GeoGebra on this one. So I've done a little bit more work here. This is a little bit more complicated. I've plotted the original curve, cosine t, sine t, sine t, and that gives me this ellipse-like object that is tilted across the xy plane. And then what I've done is I've built a point, cosine s, sine s, sine s, and this point is this point rides along the curve. All right, so I have this parameter s that I can move back and forth with the slider, and what it does is it moves a around. And then I have, forget about the a for a minute here and look at this section. This is exactly the tangent vector t. It's r prime divided by the magnitude of r prime. Now, remember that vectors don't have a position, right? Vectors have magnitude and direction, but they don't have location. So if I'm going to visualize a vector in GeoGebra, I also have to tell GeoGebra where to draw it. And the strategic place to draw the tangent vector is so that its base or its tail is situated at a point on the curve. In fact, the point corresponding to this tangent vector. So what I've done is I've created this this vector b, or sorry, this second point b that goes from the first point a in the direction of the unit tangent vector. So these are just points. A is a point that's on the curve, and B is the point that represents the tip of the unit tangent vector. And then finally what I do is I build a vector out of that, and GeoGebra knows, okay, you want a vector and you want it to go from A to B. And that's what it's painting here with this green vector. If I move it around, you can see that that vector stays tangent to the curve, and furthermore, its length stays the same. What is its length? It's a unit vector. Its length is 1. Okay? So it's a little bit of GeoGebra wizardry, but not too much. I think this is manageable. So it's showing me the unit tangent vector as I move around the curve at any time s. All right. In exercise 67, we have a particle moving along a circular path, and it's a very general circular path. It has these two fixed constants, b and omega. Now, if you think a little bit about this, b controls the size of the circular trajectory. So in the image here, we can see that the radius is 3. So in the image, b would be 3. But we're allowing for b to be any positive value. And omega is what we call the angular velocity. And the larger that omega is, the more, in a sense, powerful the time parameter is. Larger omegas mean faster orbits. So let's find the velocity function, and what we should see is that the speed, or the velocity, is always orthogonal to r of t. So what is v of t? That's the same as r prime of t. And r prime of t is just the component-wise derivative of r. So that's going to be minus b omega sine omega t, comma, b omega cosine omega t, that vector. And that is synonymous with v of t, the velocity. Let's look at the dot product of that with r of t. So let's write r of t underneath, just to remind you. R of t is b cosine omega t, b sine omega t. And now look at the dot product. We see we have minus b squared omega sine omega t cosine omega t plus b squared omega cosine omega t sine omega t, and that's 0. The dot product is 0. What does that mean about these two vectors? The vectors are perpendicular, or orthogonal, I guess is the word that we're using today. Same thing. So what we see is that in this uniform circular motion, the tangent vector is perpendicular to the position vector, and we can see that here in the form of a right angle. Makes sense. All right, in problem 71, this is computational, and it's really just an exercise in understanding the notation. You're being asked to evaluate this integral, and before you can figure out this integral, you better figure out what the integrand is. What is the integrand here? It's the magnitude of this vector. That's the square root of the sum of the squares. So we take t and square it, and we take t squared and square it, and then we take the square root, like that. We can simplify this to t times the quantity 1 plus t squared, square root, like that. And you might ask yourself, I factored a t squared out of the inside and out of the square root. Why isn't this absolute value of t? And the answer is the t's that I'm dealing with are live on the interval from 0 to 3, which is positive. And so the absolute value signs have no effect, and we don't need them. So the integrand of this function is really just t times the square root of 1 plus t squared. And this is an integral that you know how to do. T 1 plus t squared square root dt. I would use u substitution and let u equal 1 plus t squared. That leads to du of 2t dt. And we can transform the integrand in the following way. We see that the square root of 1 plus t squared is going to just be the square root of u. And t times dt is just 1/2 du. Now, whenever I do u substitution, I also want to change the limits of integration if it's easy. And here it is relatively easy. When t is equal to 0, we plug t equals 0 in here, and we find that u is equal to 1. And when t is equal to 3, we plug 3 in here, and we get u equal to 10. Now we're ready to integrate, and we can integrate with respect to u and plug in these new limits and never have to go back to the t variable. All right, that's 1/2 u to the 3/2 times 2/3, and that goes from 1 to 10. The 2's cancel, and we get 10 to the 3/2 minus 1 to the 3/2 divided by 3. So the integral of this magnitude is just 10 to the 3/2 minus 1 over 3. All right, we have a particle traveling along an elliptical path, and you're asked to find the velocity of the particle. I'm going to do all three of these. How do we find the velocity of the particle? That's r prime of t. And that's just the component-wise derivative. So we have minus sine t, 2 cosine t, and 0. Those are the three components of the derivative. What's the speed of the particle at t equals pi over 4? Well, let's first figure out what the velocity vector is. Remember that r prime is also v of t, the velocity. And let's figure out what v of t is at pi over 4. Sine of pi over 4 is just root 2 over 2. Cosine of pi over 4 is also root 2 over 2, and we have the additional 2, so that's just root 2 and 0. Now, the speed of the particle is the magnitude of the velocity. And we often will see this written as script v, which I'll write in this sort of unusual way, script v. This is speed. And again, it's the magnitude of the velocity. We can do that by squaring everything. So 1/2 plus 2 square root. That is just the square root of 5/2. That's the speed. If you had units, you would say, meters per second or something like that. Now, 89 is a little bit different. It's something that we haven't talked about yet, but something that I want you to take away from this discussion, and that is that if we take the derivative of the velocity here, v prime is equal to the acceleration vector. So if we take another derivative, component-wise, we're going to get the acceleration. So looking at v here and taking the derivative component-wise of this function, we get minus cosine t minus 2 sine t and 0, like that. That's the acceleration vector. What's the acceleration at time t equals pi over 4? That's just evaluating the acceleration at t equals pi over 4. That's minus root 2 over 2. And what's that going to be? Minus root 2 and 0. Okay? This is an ellipse, and you can see that the speed around the ellipse is actually constant, but what changes is the velocity as you go around. All right. Let me check my notes here and see if I wanted to do anything with GeoGebra on that. I think I don't, so let's keep going. again, this is more, problem 94 is more just about keeping track of the notation. Given these two space curves, can you find R cross U? Just a bit of a review. R cross U is using the determinant approach for finding cross products. T, 2 sine t, and finally 1 over t. Oops, yeah, what am I doing here? It's this component and then 2 sine t, and then finally 2 cosine t. And then the second vector is 1 over t, 2 sine t, and 2 cosine t. And maybe it's been a while since we've done this. You take the I component times, all right, we're going to blot out this row in this column and do this little baby 2 by 2 determinant. So that's 2 sine t times 2 cosine t, 4 sine t cosine t minus 4 sine t cosine t, which is just 0, minus j times the quantity. All right, there you're going to blot out the middle column and do the outer determinant, 2t cosine t minus 2 over t cosine t. Let me just double check that. I think that looks good. All right, and then finally plus the k component. Now we're going to blot out the k column and do this little determinant over here, 2t sine t minus 2 over t sine t. And that's pretty much it. This particular exercise asks you to go on and do some derivatives, and I would encourage you to go back and use the cross product identity for derivatives as you work through that. All right, problem 101 is now we're integrating a space curve. And remember, to integrate a space curve, we want to just integrate component-wise. So this integral is actually just the integral from 0 to 1 of t to the 1/3, aka the cube root of t, the integral from 0 to 1 of 1 over t plus 1 dt, and finally the integral from 0 to 1 of e to the minus t dt, like that. And then whatever results from those three integrals, that's the integral of the space curve from 0 to 1. Let's do each of these in turn. Call this 1, this 2, this 3. In 1, we want to anti-differentiate t to the 1/3. So that's t to the 4/3 times 3/4 from 0 to 1. And that works out to be 3/4. In the second component, we want to integrate from 0 to 1, 1 over t plus 1 dt. The antiderivative of 1 over t plus 1 is just the natural log of t plus 1. And again, you might worry about the absolute values that come with that antiderivative formula, but everything here is positive, so I'm not worried about the absolute values. And I want to evaluate that from 0 to 1. If I plug in 1, I get the natural log of 2. Subtract, I get the natural log of 1. And the natural log of 1 is 0, so in total, this integral works out to be the natural log of 2. Last, the k-coordinate, we want to integrate from 0 to 1, e to the minus t dt. The antiderivative is minus e to the minus t, and we're going from 0 to 1 again. We plug in 1, and we plug in 0 and simplify 1 minus 1 over e. That's the third coordinate. We put them all together, and the integral of this vector valued function from 0 to 1 is 3/4 natural log of 2 and 1 minus 1 over e. Component-wise integration. For exercises, recommending that you work a selection of all of the exercises from the end of this section, and when you're finished, go over to WebWork and try the assessment for Chapter 3, Section 2. Thanks.